Alright, ladies and gentlemen, so in this video we're going to look into radioactivity and half-life. Alright, and it's continuing our focus on exponential growth and decay. And again, these should not be new terms for you, but we're going to dive a little bit deeper into some of this material now that we've gotten into the calculus side of things as well. So let's take a look here for a second. Our goals of this video are to define, as you can see, a handful of definitions on the board here at the moment. Define what radioactive decay is, what radioactivity is, and half-life. But we're also going to go into specifically, alright, how to find half-life of radioactive substance. So let's think about radioactivity for a second. So when an atom emits some mass as radiation, the remainder of the atom reforms to make an atom of some new type of element, right? And so when it goes through this radiation, it goes through this change, we know it as radioactive decay. So the process of an element going through the radiation and the change is known as radioactive decay. That's what we see. Alright, and then we classify an element as radioactive when an element whose atoms go spontaneously through the decay process, we can then consider it a radioactive element. Okay? And so, I mean, we're diving pretty deep on into some science stuff and things of that nature, but how does it really relate to calculus specifically? So, experiments have shown that any given time that the rate at which a radioactive element decay is approximately proportional to the number of radioactive nuclei present. Thus, the decay of radioactive element is described in the following equation. And this is where our focus of calculus comes on into play. That proportion between the number of radioactive nuclei or radioactive element or matter, whatever you want to call it, is present, goes through the process, and we can think of it as the following, right? So we have dy dt is equal to the negative k times y, as long as k, alright, is greater than 0, right? But, you know, we have that negative aspect in there. Reason why k has to be greater than 0 in this case is because we need it to stay negative, because that's what makes it a decay process. And so really, when we look into this matter right here, this is really just kind of showing, alright, the derivative, right, or the instantaneous time of this decay process. And that's what we're going to be looking into in this relationship into calculus. Alright? And so, if this is our derivative, or kind of the instantaneous part of the things, you can start to see at a time specifically that we're dealing with, right? We can take that one step further above, and we can make the concept that, oh hey, if I want to really find what y is with respects to t, well, y with respects to t would then be y equals our y naught times e to the negative k times t power. And so this is where we get our exponential growth and decay formulas from. Obviously the negative will represent it being a decay in this situation. And so it's kind of interesting to kind of show the relationship with some things that we've learned in Algebra 2 and pre-calculus and how they relate to calculus as well too. And so the last little definition we're looking through is the half-life. The half-life of a radioactive element is the time required for half of the radioactive matter to actually decay. So one more time. Half-life of a radioactive element is the time required for half of the radioactive matter to actually decay. So let's take a look at an example as to how to find the half-life and use some of these concepts in calculus. So it says find the half-life of a radioactive substance with decay equation y equals y naught times e to the negative k times t, and show that the half-life depends only on k. Interesting little part in there as well too. All right, well, let's really start to think about what this is. Remember, the half-life is the time that it takes for half of the radioactive matter to actually decay on down. So the half-life is the solution, really, to the following equation, right? So if y normally is y naught times k, or times e, excuse me, to the negative k times t power, well, half of the matter is going to be when this equals half of your original amount, or y naught. All right? And so now we want to go ahead and find specifically what's happening here, because we want to find that value for t. Well, the good thing is when I divide through by y naught on both sides, they're going to cancel on out, and I get e to the negative k times t equals 1/2, and then we're getting into our logs. So we have to natural log both sides. By doing so, it basically is our identity formula that gets the negative k times t down off of the exponent. We get the natural log of 1/2 here. Well, if I want to go ahead and solve for t, I would divide through by a negative k and divide through by a negative k over here. And in the end, I see that t is equal to negative 1 over k times the natural log of 1/2. Or you can also sit there and write it on now to a different extent. Because it is that negative, I could go ahead and just switch it on now, and using our log properties, write it as this as well. Okay? And so, and again, guys, this is, let's kind of put a little side note here. This is just using our identity of the fact that, hey, the natural log of 1 over a is equal to negative natural log of a. And that's kind of just a little bubble side note into some refresher course of our log functions and log identities here. So what does this actually mean? Well, this value of t, whatever the value of t is, right, is the half-life of the element. That's how long it's going to take for this particular matter to decay, half of it to decay. But remember the second part of the problem? The problem is to show that the half-life depends only on k. Well, by having only k in our final result, well, of course the time only depends on k, because there's no y naught anymore, y sub 0 anymore. That's not in the problem. And so once that's not in the problem anymore, the only changing factor for time is your constant of decay in our constant k. All right? And that's going to lead us into our definition of our half-life. The half-life of a radioactive substance with a rate constant k, as long as k is greater than 0, we can say that our half-life is equal to the natural log of 2 over k. Okay? So we looked on into a very interesting way to approach it, but we basically derived this formula for half-life. So the half-life is the natural log of 2 divided by k. So I want you guys to give one a shot on your own. Now, it is going to be number 21 in your textbook. So number 21 on page 357. Give that one a shot on your own. You'll see the answer is 90 in the end, but give it a shot and see how you do. And we're on to the next one.